Yeah, a bit of false advertising. Yeah, I did switch the title here. It was physics and math. That's why I advertised, but now I'm saying math and physics. But okay, well, what is the difference? Actually, the difference is mathematicians typically don't know anything about energy scales. They know about equations. So they can do anything with an equation, but they have no sense about the energy scale. Okay, so, and that kind of applies to me, although I am learning. So, okay, so let me give you a little tour through some of the kind of ideas and concepts that I've worked on. Actually, it's over the past 10 years. I got into this business in 2014. I was a PI of a Moiré on 2D materials, which I thought was really great for a guy that's really good at numerical analysis in 2D. I always hate, So, and I had a great team. I had Philip Kim and Tim Kixiris. We went and visited at Harvard for a year. And then, of course, in 2018, as I'll describe, all hell broke loose with the discovery of correlated states and twisted bilayer graphene. So actually, I started developing my methods and theories not knowing anything about what the physics community had been doing, but I have connected, and you'll see. Anyway, that's for the mathematicians at least who don't know anything about this world of 2D materials. Let me just kind of review very quickly. Here's like that graphene is simply a single layer of carbon atoms that forms a hexagonal structure. So it's a hexagon is not a lattice, it's a multi-lattice, two lattices, one shifted on another. The lattice vectors A1 and A2. And if you're going to do, and again, being a kind of an old numerical analyst, all the methods that I learned in studying finite difference methods, it's a very good training for studying condensed matter physics. A lot of really the same methodology is working. Normally in finite differences, we have rectangular grids, but in materials, you have you have square grids, but now we have to look at these non-square grids. So we have to produce reciprocal lattice vectors. And so, and this over here on the right is the reciprocal lattice vectors for the graphene lattice. And we see this hexagonal fundamental domain in reciprocal lattice space called the Brillouin zone. And the amazing thing here is if I graph the eigenvalues called a band structure by physicists, then the interesting kind of points from the physical point of view, the band structure, the eigenvalue structure forms conical points at these what are called Dirac points. So that'll be very important. And so if we just kind of localize a wave packet at a Dirac point, we have some kind of Dirac equation, not the normal Schrodinger equation. So actually, in my early work on this subject, the idea was actually there was an article by Andre Geim about, hey, we should look at heterostructures, and I read that article. It was very inspiring. That's already long ago, and so the simplest heterostructure is twisted bilayer graphene. It's putting one layer of graphene on another, just stacking. I think the first kind of creation of this material was up at Columbia and Jim Hohn's group, right? Maybe it was a bilayer on hexagonal boron nitride. But anyway, what you see here is one hexagonal structure twisted on another. And what is the Moiré scale is you have an interference and you have a longer scale pattern arising. And that Moiré scale is described by these Moiré scale lattice vectors. And so, and these lattice, okay, so we have one lattice on another twisted by another lattice. The Moiré lattice vectors, as we'll see, are of scale 1 over theta. So when theta gets small, we have very large scale domains. I say it's another length scale. It's a new length scale, and that accounts for this whole new world of physics that's been unlocked, by these 2D materials. Okay, so the most fundamental model in this business is the Bistritz-McDonald model that was published in 2011. And so in terms of like connecting to the physics world, I was lucky enough to have a collaboration with Alan McDonald, thanks to the Simons Foundation, actually. And so this, I'm going to describe the Bistritz-McDonald model from kind of an applied math point of view. So from the applied math point of view, if we create a wave packet, remember, let's go back here. And so I create so on a single layer, I create a wave packet concentrated at the Dirac cone. And then I have another layer twisted. So I have these two wave packets, and then they're going to interact. They're going to interact, and they're going to be essentially, there's going to be an interference due to the other layer. And so we carried this out, again, using methods of numerical analysis, things everybody in the 3rd and 4th floor should know about. And so we showed that through the proper scaling, the Bistritz-McDonald model really emerges as the unique second order model. Okay, so it's it's a privileged model, and we derived error estimates, all that kind of business that we mathematicians do. And we show that this model was accurate for wave packets up to scale epsilon to the -2, where epsilon is the width of the wave packet momentum space, or the energy of the wave packet, because we have a Dirac cone. And so these waves, like there's waves on the layer 1 and layer 2, and they're scattering, and the scattering, again, so we have the so-called Dirac equation for the propagation just on a single layer, and we have a Moiré scale interaction T, okay? And so what is that Moiré potential? That Moiré potential is simply, you take these two Brillouin zones, one for each layer. This is the fundamental domain in momentum space. You twist them, then you just have the translation under theta, and then you create a potential of a much larger length scale. Okay, so we carried all this out. Yes.
Weird. On outflow, the toggle switches. They're no interested. Okay. So is the wave packet on a spatial scale that's smaller than the Moiré lattice vector?
It should be actually on the same scale.
The wave packet is much larger than the interatomic scale, but it's somewhere in between.
Actually, it's nice if theta is equal to f. 1 over epsilon is the width of the wave packet, and 1 over theta is the Moiré scale. So yeah, so that says that 1 over 1 over epsilon, the wave packet should be smaller than it shouldn't just smear everything out. That's the thing. It can't be too big.
The wave packet sailing around and feeling a potential that varies on the Moiré lattice vector.
Yes. I'll show you some pictures in a minute. Yeah.
We didn't.
Yeah. Good. Yeah. Okay.
Maybe you'll get to this, but what goes wrong at longer time? You say that up to a time when it depends on epsilon, then the business of the by the evolution.
Well, okay, that's a good question. I mean, nothing really dramatic. It's just going to move apart. Okay, but I'll show you some things. That's a good, but they'll just move apart like any wave packet analysis. I don't think anything dramatic.
The question, I'm sorry, is that the statement that you showed was that the districts of McDonald Hamiltonian governed the time up to this time, and therefore I conclude that at longer times the Hamiltonian is not governed by the districts of McDonald Hamiltonian, but is governed by something else. And the question is, what is that other thing? Do I have to care about it?
Well, that's a good question that let's talk about. Yeah, very good question, actually. Okay, so just to kind of, again, tie in, I mean, people who are in this business, I'm sorry for boring you, but this is if I have two uncoupled layers, then this is just my band structure, my display of the eigenvalue of the spectrum with respect to the wave numbers. And then we have these Dirac cones, and then this is what was Alan McDonald pointed out, and that's rather simple asymptotic expansion. That if you add the coupling, and then these the Dirac cones from the two different layers kind of hybridize, and you form these flat bands. And so the flat band means that the group velocity of these electrons is close to zero. The kinetic energy is dominated by electron correlations. So this is okay. So this was the thinking, and then as I mentioned, all hell broke loose when Herrero published these results in 2018, showing that indeed that he did observe at this predicted magic angle, which is the magic angle where you have the flat band. He found superconducting states and mod insulator states and all this, and and since then, literally, it seems like every month or two, some new dramatic experiment is happening, and then 5 of the top guys have papers in archive within a few months. This is really a hot field. So so it's very exciting to be a part of this. Okay, so one of the things we did with Alan is say, okay, we've done this theoretical analysis. Does it really apply to magic angle twisted bilayer graphene? So we really put the numbers in. We put the numbers in, and so we found that so remember, these were the assumptions of our theorem. And so this is a scaled interlayer potential. And we wanted that to be on the energy of the interlayer should be on the scale of the energy of the wave packet. Okay, and that wave packet energy, or that the epsilon of the wave packet should be corresponding to the angle. And so we calculated at the magic angle, the scaled interlayer interaction is 0.042. The magic angle is 0.017 radians. So we're in the right ballpark. Okay, and then further, we made some other kind of back of the envelope calculations, asking, okay, these interacting Coulomb interactions, what's the energy scale of those? That's 23 MeV, whereas let me just jump down here, the flat band bandwidth is 10 MeV. So that's saying that these interactions really are dominating the physics when you have flat bands. And also it says that, and this is all hand waving stuff, that the interlayer hopping energies are 110 MeV. So in some sense, it's saying this model, this non-interacting model, is really the non-interacting part of the many body model. That's what we're trying drive for, because people are going to add stuff onto that non-interacting part, as you'll see in a minute.
Sorry, by Coulomb, you mean interactions of electrons?
Electrons.
You mean interactions between the two layers?
Yeah. Well, yes, they can interact. Yeah, but it's also through the boron nitride, et cetera. Yeah, because that's where I put this. Yeah.
They could be in the same layer or different.
But isn't that already included in part of the quasi-particle, the Fermi C model and everything? That's what I'm.
Well, it's only included in a mean field way. But I'm going to come to that. It's included in a mean field way when we get these hopping energies.
Okay.
It's not in it's in a very coarse way. In fact, that's a good question, because one of the big arguments in I'll come back to that. Okay. That is a question. Okay. So we've played around. Here's our here's our bands for the Moiré length scale. Here's our flat bands, and so we just put some wave packets on the higher energy bands, which are not flat, and then we'll also put a wave packet on the flat band, and so when we and so as expected, when you put a wave packet on the non-flat bands, then they just kind of they move. Okay, here you go, and this guy's moving. Okay, and that corresponds to the what I would call the first principles model is we take to be a tight binding model that's obtained from Varney basis functions that are parameterized by DFT, et cetera, et cetera. Okay, so now here, this is more interesting. If we put a wave packet on the flat band, this is for the tight binding model. You might say I assume we'd get something the same with DFT. Then we actually get some kind of swirl here. Okay, now the Bistritz and McDonald, that kind of vorticity, or whatever you want to call it, is not present. But then what we've been doing now is actually trying to take this model, and it's related to Andy's question. We're really expanding it to all orders and including relaxation. So a full exploration of the model. I should mention that the program will include all 2D materials eventually, as much as we can do. But our second order model includes this vorticity that's missing from the Bistritz and McDonald of order 1. Okay.
Good question. I mean, you're not taking into account the fact that the Moiré scale is not translation there. I mean, there's no translation of variance actually on the Moiré scale. So you're assuming that.
No. This is all continuum. This is all continuum scale. Yeah. I'll come to the non-continuum stuff in a bit, but that's right. That's not here yet. Yeah. And I should say, what we're doing. And this again back to my comment about energy scales. So Vafek has a similar program. Oscar Vafek, who's spoken here several times. He's written, 2 really beautiful papers. Does in the end get some similar results to what we get. Again, being a physicist, he throws out terms based on their energy. Being mathematicians, we kind of use epsilons. Okay. Okay, just a little bit of a culture. Yeah.
What's the relationship of this to the previous thing you said? You said that the standard Bistritz and McDonald model describes evolution up to some time, which has to do with epsilon. And here you're saying that over time with 5 and some units, I get an evolution not contained in the Bistritz.
Very good question. Very good question. Okay, that's a very good question. That jogs what I should have said early on. This second order model, the first order model is an accurate epsilon. Its accuracy is epsilon squared times time. This model is epsilon cubed times time. To get an epsilon, to go longer in time, we have to have another scale in time. Yeah, normal asymptotics, right? You need to have, you have to do, you can't just have a one scale in time. So that's what needs to be done.
From physics point of view, are you going towards the chemical potential at going to lower energy?
I don't.
Usually to us, longer time, lower energy.
Well, I don't think, well, there's no radiation or something. I don't know how to answer that. Okay. Yeah.
Supposing I'm interested in very low energy.
These are just, this is just the exact equations, like I said. And then this is just, these are different approximations. I mean, this is a hyperbolic equation. There's no energy loss in this equation.
Density there. What are you talking?
This is just it's just the psi squared. Okay, it's just the wave packet amplitude. Okay. Yeah.
Saying that over time the density develops.
Yeah. So anyway, did I? I think I hit on your answer that you have to do higher scales in T, and you can get just in. Yeah.
But I guess somehow we're seeing differences between order 1 and order 2 already in time 3 and 5. So that's going back to your previous thing. Epsilon time in whatever you're measuring time, by the time time is 5, epsilon times time squared is not negligible.
Yeah, I guess that's right. Yeah. Okay, let me move on. Okay, I'm not going to get to the end, of course, unless people want to sit here for a long time. Okay, so I am. I'll use the word starting to dabble in interacting models, and it's been great to be here. And literally the first day or two I was here, I know like Paul Yang was showing me his wonderful results and things like that. So it's been fabulous to be here. This is I should say this is a true paradise for computational science, 8 floors of amazing work. But okay, so I've been, I interact with Lynn's group out at Berkeley. And so his group, and they've been collaborating with Mike Zolotel, many other people have been doing this stuff. And so the idea they have is take this single, this non-interacting models, and then you diagonalize it. And so what you really want to do is here's these flat bands. So if I didn't have any interactions, I could say, okay, let's just do a dimensional reduction and just look at dynamics projected onto the flat band. Okay, so that's what you want to do. All right, these are all eigenstates. But now you want to, now here, what you want to add to this model, and again, this is just a sum over the flat bands, M, so this is, there's okay, there's two bands in each valley. But anyway, this is simply on the flat bands. So now you add in this interacting part, and I didn't write down the formula for the Coulomb interaction, but that's where it comes. So projection on the flat band, add Coulomb interactions. People are arguing about double counting of Coulomb interaction when we come to Alex's point of view. It's something that I would like to clarify this summer. I'll be visiting LBL and et cetera. Okay, so there's a lot of work on this. What our contribution is trying to, we're working on, as you'll see, one of the things I've been most involved in is relaxation and trying to derive relaxed models. So, this initial work doesn't use relaxed models. We're trying to get that into the model in the code. So that's something that we've been doing. Yeah, so Kong I've been doing an internship out at LBL as a grad student of mine, and the guy doing all the work in Lynn's group is Kevin Stubbs, a postdoc with Lynn. Okay, So, okay, so so where was I in 2000 and what, probably 2016, 15. Yeah. So, yeah, so I had so my last sabbatical, I was a Radcliffe Fellow at Harvard. I was embedded with all these physics people. And being a mathematician, you don't start with P equal 2, right? You start with P layers. So we said, okay, we derived these, we studied the geometry and we studied general things like Kubo formulas and general stuff on P layers, arbitrary P layers, twisted, whatever you want. It's a very general formalism. We published in, of course, in these kind of math type journals. This one is particularly kind of, I would say, not readable. It's written in a C-star algebra formalism. I don't recommend it. But these incommensurate materials map beautifully into C-star algebras. Okay, you just have to define all the operations. Okay, so but this paper I think is actually has the key. This has a description of how to do relaxation for P layers of heterostructures, whatever you want. So that's all in here in a written in. It's not totally incomprehensible to outsiders. It's a very prestigious applied math journal. It took a year and a half to get refereed, of course. But you know, and then so we developed these kind of you know, math, an approach to P layers. And it turns out that the last several years, you know, people are getting interested in all these new platforms and many layers. 5 layers is hot now. Okay, our kind of most of our activity was in tri-layers. Okay, and then I must throw this out. This was sent to me by Angel Rubio. Actually, I think when we were writing our Simon's proposal, and of course it includes many of the people here. And this is really, this slide is sort of my inspiration. Just this idea of, oh, you just have all these different Moiré structures you create. And it's sort of like you create all these new Hamiltonians. And then you get to study all these different phases. And so and again, that's really going on right here, you know, at Flatiron, thanks to, you know, Shiwei and Morales, everyone. Paul was explaining this to me. I think you guys were working on this here, right? Just you were actually computing all these phases right here, just with a little parameter in the Moiré potential goes from here to here and everything in between. Like what? Try it. Okay. Yeah. Okay. So now let me get a little bit of some math theory and not scare anybody. So mathematicians like to, you know, define things. Physicists like things to be understood in their context. I think that's a correct statement. But I think that's what you said, Andy. I think other day, right? And I've tried to adopt some of my language. Okay. So when I talk about a lattice, you know, I use R sub j to mean a lattice vector in layer J. It's just, you know, for calculation, it's just a matrix whose columns are the lattice vectors times a vector, an integer vector that spans all the lattice vectors. I call script Rj the jth layer. Then sometimes I have need to describe the unit cell or fundamental domain for the lattice. I use D for domain. Yes.
You allow every layer to have different lattice vectors.
Oh yeah, quite general.
We're not dealing with the homo.
No. And you could have as many sublattices and orbitals, whatever you want. Yeah.
At some point, you will insist, I guess, on commensuration.
No, I won't commence. No, not at all. Okay, I hate commensuration.
But then, do you really have a Brillouin zone in that case?
Well, it's coming.
Okay.
That's coming. Yeah, it's exactly good question. That's amazing how many people ask that question. Okay, so here's so reciprocal lattices, physicists like to use G. So G sub J are reciprocal lattice vectors for layer J. The unit cell of the reciprocal lattice is called the Brillouin zone. I kind of call it J sub Z. Okay, so that's it. Now, okay, so here's the definition of incommensurate. Nobody's asked what the definition is. The definition of two incommensurate lattices are that the sum of a vector of a lattice vector in say layer 1 plus a lattice vector in layer 2. This is 0 if and only if both lattice vectors are 0. Okay, it's this is the definition. It's equivalent to saying if I have these two lattice vectors, if I have the reciprocal lattice vectors, and I have both of them plotted together, and you drop me down on one lattice vector, I can't tell where I am. Actually, I can tell where I am in the incommensurate case because every environment's different. In the commensurate case, it's all the same. It's periodic, right? So okay, and so the fundamental theorem that's used everywhere in my work is in fact that if you take a function that's periodic on let's say lattice 2, okay, and then you sample over lattice 1, then the average converges to the to the integral of this function. It's the average of h over the unit cell of layer 2. Okay, so what does that mean? It means that, okay, let's go back over here, and here's one layer twisted on another, and so here you can see the moiré, and what I want to do is look at the blue lattice vectors. Everywhere so this green is here. That's and I draw these arrows from the lower left-hand corner, although that's arbitrary, of the red lattice, okay, and then this is called the dysregistry in mechanics, just two materials, one on another, and then as I move through this moiré, this dysregistry uniformly samples the red lattice. Okay, so if I'm incommensurate, then when I plot all these dysregistries, it's going to be finite, but it's going to uniformly sample. And then if it's actually incommensurate, then if I go to the next moiré cell, it's going to be slightly modulated. Okay, if it's commensurate, they're just going to keep hitting the same point. Okay, so in the incommensurate case, I have this. Yeah, so what that says, for instance, what can I do with this? I could say if I have we've done this. If I have, okay, in mechanics, you have something called a site energy. It's the energy of an atom, mechanical energy of an atom that depends on its nearby neighbors. And then if I can use this theorem to derive a continuum elasticity model. If H is a local density of states, I can compute a density of states. We'll see all this. Okay.
Just so I understand what's being said here, what's the meaning of the arrow? Is it in particular I'm taking little R goes to infinity, so I'm sampling over the entire space of one layer?
Okay, so you understand that if I go to any blue.
I'm just the line above. It's a very low level question. What is the meaning of the arrow? You say sum over H of R goes to. Sorry. This for every. So what is R is just some ball, gigantic ball. But the meaning of the limit is as the gigantic ball goes to infinity.
That's right.
That's all I wanted to say.
That's right. That's right.
Thank you.
Right. Or if you want to take it in the ergodic point of view, think of, okay, you're sitting there and you're on these blue lattice and you're the drunken sailor and you're hopping around and you're just counting this registry, okay, and that everything is converging. And to prove this, it's actually simple Fourier analysis, so you can do it, okay. Anyway, so let me. Okay. So, but the point is that this is the condition. Okay, so now I want to describe okay, so here, to make it a little more formal, the disk registry of an atom or lattice point, I should say, on layer 1 with respect to layer 2 is simply R1 modulo the lattice on layer 2, right? Or just, okay. This is just exactly what I explained there, so don't worry about that. So the disk registry is really defined as with respect to a point. Every point has a disk registry with respect to this this lattice. Okay, but now I want to so I gave special meaning to the value at the lattice points. But now I want to, if I just move through the material, this registry will oscillate on the atomistic scale. But if I interpolate off the atomistic scale, I get a smooth function. So that's the continuum disk registry. And so that has this is the formula.
Why are you allowed to smoothly interpolate?
Because if I don't interpolate, if you just say, if I just move between atoms, then the disk registry is oscillating on the atomistic scale. But the disk registry of two nearby atoms is very close, right? It's because they're smoothly varying. If I take, say, a small angle twist, it's smoothly varying. Okay? Yeah. So, okay. So then, okay, so here's another little picture from a paper I just wrote on showing this notion of disk registry. Okay, so now here, now I've defined the notion of disk registry. They're just mappings of R2 to R2. Now these fundamental domains, sometimes I think of them as like as kind of sets in R2. Other times I like to think of them as tori. But let's think of them as just these sets I described in R2. Yes. No, not at all. Not at all. No, that's fine. It doesn't matter. Here, look.
You want to know, do they both have honeycomb or a square lattice?
That's fine. That's fine. Yeah, because all that really matters here. Yeah, here, look. This is my mapping, right? And so that's all incorporated in the lattice vectors of A1 and A2.
The length, I was just curious, the geometry itself, the lattice vectors.
Yes, yeah, could be, yeah. In fact, I'll show you some examples in a minute. But okay, so so literally, if I take the special, this just says if I go back over here, and I say okay, and I've done this interpolation, and then I go and I say okay, I look at the inverse of the function of this disk registry, then that uniquely maps onto this continuum Moiré cell. Okay, so my point is that the notion of a Moiré cell, a Moiré superlattice vectors doesn't need commensurate structure. In fact, the theory works best if it's not. Okay, okay. So yeah, so it's because what you have is you don't have periodicity, you have a modulation around periodic. It's a slight modulation, but you might say the average, it kind of averages out to this cell as you go. Okay, so there's ways to look at it. But okay, so let me now, okay, here's just an example. Okay, here's the famous twisted, bilayer A1, A2. Then you just do that calculation. I calculate the lattice vectors for the Moiré, and it's just simply the lattice vectors for the original lattice scaled by 1 over 2 times sine theta over 2. Okay. Now, so now let me talk about the models. This is again more for the mathematicians. So these interactions called hopping functions, tunneling functions. If you just want to look at it as they're just like finite difference interactions, you just have, think of just having a graph. You have a graph and you have some connections. So we can define, so the way you do it is you kind of get, you have your, let's say your mean field DFT, you create what's called Varner basis functions. Then you can parameterize, then you do a few positions, and then you parameterize based on symmetry. But and you end up with some, I'm just, for simplicity, I'm going to talk about these two center approximations, although more general approximations are possible. So then I can define a Hamiltonian simply this right through these hopping functions. Okay. So then let me just give you a simple, numerical method already we can talk about. Let me just say, okay, if I take we have R1 and R2. Those are the two lattices. And then B sub R is just my cutout of radius R. And let me call omega sub R is like this projection. Okay, so now I have this, now I actually have this, a matrix Hamiltonian. Okay, now let me point out a really key thing. When I talk about these two layers, there's a free parameter. The free parameter is there's a shift vector between the layers. I want to talk about an origin, and there's a free parameter in that shift, right? You get little differences depending on how you do that shift. And that's going to come out of our method. So, okay, so what is an approximate density of states? Well, an approximate density of states, I want the density of states at E. It's approximate because I use a Gaussian, and then I just take I take the Gaussian applied to the Hamiltonian, take its trace. Then I get an approximate density of states. And then I can also define local density of states, et cetera, right? These are, and density of states is a measurable quantity. Okay, now here's the thing is I can talk, okay, this says, this notation is, okay, this is the density of states at these blue lattice points. Now, what I claim is I can, rather than, okay, so one way to do this problem is take a big gigantic matrix with radius R, diagonalize it, and then get all the properties from that. Well, if I did that, the problem is you have a lot of errors because of the boundary effects. So the idea is instead of having a boundary, this thing will converge like 1 over R. You can get an exponentially convergent method by not having a boundary and simply going and sampling like every blue lattice point. I actually create a little cutout with no boundary, and I call that the local density of states. Okay, and then I can average all of those to get a density of states. And so so what I do is I just talk about a density of states at the origin with shifting the initialization, right? So okay, so if I do that, then if I want to look at the density of states, that just says, okay, I just average over the local density of states over the whole domain. I use that ergodicity property, and I actually have a formula. So what this is okay, but this is an exact formula for the. So what we end up having is an exact formula for the density of states for two incommensurate lattices. Okay, now I don't think anybody, we kind of published this in 2017, blah blah blah, but nobody had ever actually done that, as far as I know. I mean, again, if you're a physicist, who cares? But I always say it's sort of like showing irrational numbers exist. Okay, there you go. Okay, so now, so we use a method that is quite popular here, I believe, the kernel polynomial method. So it turns for people who I'm sure everybody here knows, they just want to compute an approximate delta function. You have a double Chebyshev polynomial. You have to smooth it out a little bit with what are called Jackson coefficients. And then you scale to get the proper appropriately. So we can compute our local density of states as simply just an integral over that fundamental domain of that smooth that smooth delta function with respect to all those shifts. And then so what this is the density of states this is just a trace element, right, at 0 with respect to that shift. And that's just computed by this double Chebyshev expansion. So what my point is, to compute the density of states for all energies, all we have to do is actually calculate, is to do this Chebyshev for some sampling of these various shifts. Okay, so and again, being mathematicians, we did an analysis of all the error, equilibrated all the error, and this is actually a very efficient method. Okay, so now let me go to something more interesting, and algorithmically for sure, and that's you can apply this method to things like Kubo formula, various topological formulas for topological index, all that kind of stuff. So again, for the mathematicians, what is Kubo's formula? It's just a way to go from from a Hamiltonian, electronic Hamiltonian, to a conductivity. It's a linear response, right, to an electric field. Okay, and this is the formula, right? This is in the traditional quantum formalism. This is a density matrix at temperature beta, and this is your Fermi-Dirac distribution. This is our operator, right? This is our linear response operator. You take the trace. So this is okay. So and then you could put that into maybe a more common formula, which is essentially summing a conductivity function, right, which has a bunch of nasty poles, times what's called a current correlation operator. Okay, so let me just point out this might be of interest to somebody here. We actually wrote a paper a year ago. There was a 50th anniversary of Japanese Siam journal. So we thought, okay, what better to do than send them a mathematical derivation of the Kubo formula. So I think this is kind of hits a nice tone between some of the really hardcore, unreadable math physicsy approaches and some hand waving in physics. So the main thing is you kind of have to put that dissipation in, alternating with the transport and do it right. And there's quite some subtleties in what are called Tauberian theorems. So I kind of mentioned that. Okay, so pardon?
I won't say anything about specific. Let's say the limit of zero energy is the weight of sigma finite, zero portion to the size of the system, and one kind of thing that we are usually interested in. And the general results.
Let me talk to you. I'm really running out of time, and it would take me a long time to understand your question. Okay, so let me just, if you don't mind, yeah. So,
where is the dissipation?
Oh, the dissipation is eta.
Okay, but I could also call it adiabatic switch. So does it matter? You're saying eta is finite and has some physical meaning here. It's not.
Yeah, yes, it does have. There is a term in our operator. Yeah.
So it is microscopic. It's not a phenomenological.
No. Okay. So then if you just do you let R go to infinity, and then you derive a formula for Kubo that I think that people are probably most familiar with. Okay. Now the question is, how do we generalize this to incommensurate multilayers? So this is kind of, you might think this is like our project is kind of like how to formulate a lot of things in this incommensurate setting, like we're working on phonons. I don't think that's been really done correctly in incommensurate setting. And by that I mean like really everything nice, okay? Mathematical foundation. So anyway, let's just go here. So how do we do a configuration or dysregistry base, an incommensurate Kubo formula? Well, what we do is what we did for local density, for density of states is we took an integral over local density of states. So now I'm going to do an integral over local conductivities. So we have to, so this is, here's my my conductivity. Then I have conductivities that are, we have to integrate over the conductivity with respect to local environments. Okay, so let me talk about how this goes. So this leads to a lot of interesting mathematical problems. So this is my conductivity formula. Remember, it had those poles in it. Okay, not a nice beast. So what we do is we do a double Chebyshev approximation. Okay, so let's say we have this approximation, and then the question is, what indices do I use? It turns out that a double Chebyshev approximation multi-D is actually quite a beast. As, you know, 1D it's quite nice, but it's really quite a beast. So, but anyway, so we were able to kind of actually derive what I call an approximate. Just means we have this finite R, because we're just at some point we have to do cutouts. But again, we're never solving an eigenvalue problem. We're just doing Chebyshev on these operators. So this is my formula for a given dysregistry. I mean, I'm summing over layers, over orbitals. Then I sum over the Chebyshev coefficients. I have these guys, CK1, CK2, and then this is my current correlation operator that I need to. So I need to compute all these guys, multiply them, take the diagonal element, and so anyway, so we okay. So this is an approach. No, I'll come to that. Yeah, in a minute. So okay, so this problem has a little bit of a history, because I'm not sure if Andy remembers when I first met Andy. He came to Minnesota. I don't know. I was showing you something, and he said, "What is this local conductivity or something?" I don't know. You asked me that, okay? And I didn't have a good answer as usual. But it turns out, you know, I was actually at Stanford in February, and I met one of their postdocs, Judy G, if I'm pronouncing her name right. I don't know. And from her, I learned that local conductivity is measured quite a bit in these 2D materials now, and it's done by this technique of they call it microwave impedance microscopy. Okay, so in fact, this is and I actually quote this from this article I got. Actually, Judy sent me these things. So it says, okay, it says our results demonstrate the usefulness of microwave impedance microscopy, and yeah, basically it says it's really the local conductivity. Okay.
But I'm sorry if we asked the question from me.
Yes.
But therefore, is the meaning that I apply a more or less spatially uniform time-dependent electric field, and I measure the current as a function of position?
Yes.
Ratio of those two things.
Yeah. Yeah. So, yeah. So this now, okay. I at one point I kind of worked it out. Now, for those who I'm sure those who teach freshman physics know all about impedance, right? Okay. So so it has a real and imaginary part. I think it's the imaginary part that connects to local conductivity. But this is measurements, and so this apparently is quite a big business these days. So a lot of papers coming out on this. So so what I haven't done is actually, we've done some numerics on this method. We've certainly not done the full computations, especially we haven't even developed the algorithms to include relaxation, which is really important. Okay, so, but anyway, here's the method. The method is, here's our algorithm. Again, we take these, essentially these are just, so you concentrate at the origin, and you apply these operators. And so then the big question is, okay, what Chebyshev coefficients do you use? And it turns out this is all the computational work. Again, so again, so then here, let me just, okay, so I'm running out of time, but anyway, so, and then there's this question of dealing with these poles and pole separation. And so we've actually done, and there are some problems in this at low temperature. I'm not sure how low temperature you can really get with this method. Actually, if you just go straight momentum space method, I think you get around the pole problem, but you have other problems that's more restrictive. These methods can include at least some uniform defects and things like that, which I don't think you can do with momentum space methods. Maybe we can talk about that as well. But okay, so all those, remember, I'm averaging over these cells corresponding to this registry, but I can throw in some distribution of defects as well. I mean, it's a sampling process. That's a good question. I don't know. Yeah, but okay. So here's these are just the I do the expansion at different temperatures, and you see at low temperature you really only need the diagonal part of the expansion. But okay, let me just run through all this. Okay, now okay, so probably most of my work may actually be in relaxation, and I always go back to this beautiful paper by Paul McEwen. And so, okay, so basically, if you put one layer on another, two lattices on another, they want to structure relax. That's not essentially, atoms don't want to sit on top of other atoms. So what you really like is this, what's called Bernal stacking. That's this, AB or BA stacking. And AA is when they all sit on top of each other. So this is my energy landscape of one layer with respect to the other, moving it around. And so this just, again, so anyway, so this kind of motivates, say, developing a continuum model to essentially simulate this at the continuum level. So I want to point out here, this is quite interesting. We've done a fair amount of work on this too. This is actually an experimental, well, there's two things here. This is a electron diffraction. This is a dark field imaging, okay? And this is a beautiful technique, because with this techniques, I'm just amazed. You can get, so so essentially, instead of being uniform, instead of the dysregistry uniformly moving, you want to kind of create these large commensurate domains with little interfaces. And I'll get to that in a minute. I won't get that to a minute, but because I'm going to run out of time. But let me just throw out another interesting applied math problem for our analysts in the audience, if there are any. If you take so actually, I think all the information is really in the diffraction pattern, right? Because, right, I mean, diffraction is sort of a Fourier transform machine, right? So, and if you take two layers and they don't interact, then you essentially create two sets of reciprocal lattice vectors rotated. And now if you add relaxation, you get these, I think people call them satellite peaks. I mean, and the question is, can you actually extract from the diffraction? So everything in that diffraction pattern, there should be enough information to back out the atomistic structure, right? It should be there. And so, I played around. I had some formal work stuff I did with a postdoc, Paul Cazot, something that maybe all physicists know about, Jacobi Anger expansion. Is that common? It's how you change spherical waves into plane waves. Is that textbook stuff? Yeah.
Yeah, although they don't call it that in the
Okay. Anyway, I just want to give that to some harmonic analyst, see if what they can do with that. But okay, so and this is a recent paper we wrote, so again, this is the unrelaxed structure. This is the relaxed structure. What you want. This is kind of showing you kind of what you want to do. You want to restore these. It was called AB and BA. There's two symmetric structures. And this just shows you the difference when you do when you do the band structure. If you do let's go focus here on the magic angle, then you have a minuscule gap here. Remember I said it's nice to have a flat band and some nice gaps between the other layers, but this gap's minuscule. But it turns out if you add the relaxation, you get a nice gap, and so you can, yeah. So actually, in this case, the relaxation really does make a difference. And then now we also developed this theory of relaxation. And let me also, okay, what this is based on, okay, the first question you have to ask yourself is, okay, if I really have an infinite system, then I say, okay, should the displacement be periodic on the Moiré? Who knows, right? And in fact, and this was a kind of related to something called, I think physicists were apparently interested in at one point problems like this, and mathematicians, it goes under Aubry-Mather theory, and so we kind of so in the end what we show in 1D and what we assume in multi-D. Okay, so in 1D, the question is this: the displacement, we say, depends only on the dysregistry, on the local environment. Okay, and that's provable in 1D. Okay, if the interaction is small. If the interaction is not small, then that can break down. Okay, it's interaction with layers. It's kind of related to KEM theory, things like that. Okay, so okay, but let's just assume this. I just throw this out for mathematical. There's lots of interesting questions at the foundation at this subject. Okay, so we have our so we can formulate a continuum energy in terms of displacement that's now periodic on the Moiré, and so we have our interlayer terms, normal, like linear and nonlinear elasticity, whatever you want, and then we have interlayer interactions. You have a misfit energy that, say, of layer 1 with respect to layer 2, that's depending on the dysregistry and vice versa. Okay, so if you do that, and then you properly scale and use some, and you get some kind of Ginzburg-Landau theory. And in fact, what we show is that as the angle goes to 0, the thickness actually converges to a constant, 5 atoms or something, okay? And so you really have a very sharp domain. And why? Who cares about that? Well, the reason that's important, I'm going to finish in a minute. The reason that's important is that if you're going to do electronic structure, and now you've got you no longer have a smoothly varying, you're no longer scattering off a smoothly varying periodic structure. You're scattering off a very rough structure, and so this is our our interlayer scattering. So this is the scattering in unrelaxed. And then if I do the Fourier transform now for a rough function, I actually turns out that I scatter into all these higher modes. So in Bistritz and McDonald, we only scatter into the nearest waves, okay, in momentum space. But here we have to, and so we actually, with our methods in our analysis and numerics of the relaxation problem, we're able to actually quite accurately describe what kind of model you need for electronic structure. at small angle. And in fact, you need to scatter into 1 over theta a wave number. So you really, yeah. So so here we've done all the yeah. So these are just these results are showing you say starting the Bistritz-McDonald model just says, okay, I just scatter to the nearest neighbor in momentum space. But here I'm studying scattering into longer range scattering, and also how big a matrix I take in the first place. So all those are questions to ask for accuracy. And so we've got all the, we've got dependence on theta for all these things. So anyway, with that, I think, yeah. So, okay. So with that, I thank you all for your great questions and attendance. Bye-bye.
Yeah, so I guess the idea is instead of density states, instead of integrating over sort of giant Moiré cell box, that you can integrate over this.
Well, yeah, the picture says it all. Let me just go here.
So I guess my question is, how do you sample this registry? What tells me how many points I actually need? Why is that less than?
Well, this registry is that's a yeah, it's a smooth function. So so it's kind of.
But is there some? Yeah, does the number of points I need to sample that scale?
Well, here, right there. So this says errors will be balanced if how large a cutout I use at that local environment. It says it should scale like the number of how I sample the dysregistry, and scale like p log p with respect to the kernel approximation. Okay. So and we have in our paper we have all kinds of numerical tests showing this is really true. Okay. So but let me just say this is, I mean, it's like one of these things that once you get into it and you say, oh, maybe it's not so hard after all. Maybe it's obvious, who knows? But yeah, so the thing is let me just distinguish between the brute force way is just to take a huge domain and then compute eigenvalues and eigenvectors, but you have all these environments on the boundary that are screwed up. But now what I'm doing here is I'm never treating a boundary. I'm just going to every environment, and it should be bigger than this, but let's just take some little cutout of every one of those, right? And then there's locality everywhere. The Hamiltonian is exponentially decaying off.
So that big box length scale, you're saying really disappears.
It disappears. Yeah. In fact, this was one of our early things. Is we can compute. We have very accurate like density of states down to 0 angle. Okay. Yeah. And let me just say, a lot of what people were doing before this is I said, okay, when I got into the business, I saw people doing band structure. They'd say, okay, here's like 2 different, it was actually, I think, a heterostructure. And they say, okay, I take one of them I stretch in, one I pull out, and I try to get them into some periodic structure. It was incommensurate because it's a heterostructure. Then I try to strain and stretch to get them into a periodic, and then I hand it off to my band structure code, and I print, and I have all these beautiful results. I said, okay, that seems kind of hokey to me. I mean, so I said, can we develop something that that's honest about the incommensurability?